I don't know for you, but I saw a presentation like Wednesday by Vincenzo called A Sandbox Odyssey. Is Vincenzo in the room? No? Okay, maybe I'll arrive later. Basically, he advocated that in a couple of years, sandboxes will not be so important anymore. The reason for that is that because what the attackers are interested in too is the data. And basically the data sits in the cloud more and more. And over the coming years, it's going to be more and more like this. And from a browser sandbox, you can access the cloud, right? So you don't need to break free of the out of the sandbox to get access to data, which makes sense, and I kind of agree with him. But the catch is that he was speaking about sandboxes in browsers, and this talk is about the sandbox in Adobe Reader 10. So of course, in that case, you still need to evade the sandbox to get access to data in the cloud or whatever, because you don't have access to the cloud from within Adobe Reader if you stay in the sandbox. So this talk is basically about evading the Adobe Reader 10 sandbox. We will show an exploit, but the whole talk is not really about just the exploit. It's just more about a method and some input, some insights, so as to how audit some parts of the sandbox and how to find vulnerabilities in the sandbox. So I was supposed to present with Eric Liu, but he couldn't come because of some visa issues. Basically, he had the original idea, I did the original research, I just contributed to some parts and helped organize everything into a consistent paper. But the true genius in that business is Eric. So that was for the disclosure part. And yeah, we all part of the 40R team in Fortinet. So basically, it's the threat research and response team. So the reason behind all this is this. Over the years, we've seen more and more vulnerabilities for Adobe Reader. Especially since 2010, there's kind of ramp up. I don't really know why. Maybe because people started to search for JavaScript exploits or JavaScript vulnerabilities, which are kind of easy to find in Adobe Reader. So you have plenty of vulnerabilities, but can you really compromise Adobe Reader 10 with those vulnerabilities? Some guy, Mr. Armandi, found 400 unique vulnerabilities by himself. So really, there are plenty out there. Yeah, can you really compromise Adobe Reader 10 with those vulnerabilities? Actually, not really. Since Nova 2010, we have not seen a single successful exploit in the wild against Adobe Reader 10. It's all because of the sandbox. And so the vulnerabilities make you gain control of the execution flow inside the sandbox. But that doesn't give you control over the whole system, right? Such are examples of all those vulnerabilities. And the Adobe Reader 10 protected mode, which is the sandbox, would prevent such exploits from executing. So you stay confined in the sandbox. That is why we orientated our research into that direction, to see if we could empower all those exploits and use them to later break free from the sandbox, which I think is pretty interesting and valuable. This is taken from some Adobe blogs, and it illustrates very well why it makes things very difficult for attackers when some sandboxing model is implemented. Basically, it makes things twice more difficult. Because first of all, you have to find a vulnerability in Adobe Reader in the sandbox process, which this is not very difficult. We've just seen how many of those are disclosed over the years. Of course, your vulnerability must bypass DEP, ASLR, and the like. Then to gain control of the execution flow with a high privilege, you need to exploit a vulnerability in the broker process. We will cover that afterwards, the broker process and everything, just to give an overview. Then in the broker process, you still have to bypass DEP, ASLR, etc. And since the broker process itself doesn't run with very high privilege, you still have to exploit a local privilege, privilege escalation vulnerability, and then you end up into successful exploitation. So this is how we will proceed today. We'll introduce the sandboxing model, which is loosely based on the practical Windows sandboxing techniques implemented in Google Chrome also. We'll give we'll have a look into the implementation and give some practical example how to play with all the different bricks inside. Then we'll show a fuzzer, and we'll disclose the exploit that we found during the course of our research, with a small demo and then a conclusion. If you want to delve into the Adobe Sandbox, the first information source is really the Adobe blogs itself, with all the documentation written by Carl Randolph from a set. This is really a must if you want to start with. This is a quick overview of the sandboxing model. So it's kind of basic. I mean, here you have the normal Adobe reader process, which runs inside a sandbox. So Adobe called this the PDF principle. We will call that the sandboxed process of the presentation. It doesn't have access to other things, to resource in the kernel and in the operating system. So whenever it wants a resource, it has to communicate via IPC, the inter-process communication, to a broker. So the broker is really kind of like a proxy. It's totally a proxy, actually. And the proxy, the broker, will in turn ask the OS for the resource. This is just an overview, but here's a more detailed view with all the stuff that is happening. So, as I just said, you have your sandboxed process, the PDF principle, the PDF reader, that is in charge of rendering the PDF. It runs with a restricted token, so it has very low privileges. Now, when it wants to access a resource, for example, if you want to create a file, it's going to call the Win32 API create file, right? Now, what's happening is that when you're redirected from the application inside kernel32.dll, where the Win32 API sits, usually it sends you to the corresponding native API, which in that case is nt create file in ntdll.dll, right? In that case, the entry point to that native API is hooked. And instead of nt create file, the function that is called is target nt create file, which is a function taken from the Google Chrome Sandbox implementation. Now, what target nt create file does, it queries the OS. It actually does a nt create file. The OS will say access denied because you have low privileges. So then target nt create file will call the broker. We'll send an IPC message to the broker with a tag that says, I want to call nt create file. The broker receives that message. It checks if the sandbox process is allowed to do that. So you have a policy engine here, checking do you have right to do that or not. If you have the right to do that, then it will forward the call to the kernel. So you call into ntdll.dll, the nt create file API. then you get into kernel land via interruption or whatever. The kernel returns the handle of the file we created. The broker process duplicate the handle and send it back to the Sandbox process, and then you can create the file from the Sandbox process. This is how it works. All right? Is that clear? Raise your hand if you didn't understand, because I can re-explain. It's really the heart of the stuff. Okay, cool. So how can you attack that model? How can you escape from the Sandbox process? There are two big attack avenues, I would say. You can attack you can attack the kernel land, because in the end, you're going to communicate with the kernel. Should it be here via target integrate file, or here integrate file? So the arguments are passed to the kernel as is. So if you have some vulnerabilities inside the kernel, then you gain control of the operating system. We believe that more and more, if the Sandbox model like this gets implemented in more and more products, then probably attackers and researchers will focus more and more on kernel land exploits, because it allows to bypass everything at once. And then you have all the attacks from user land. You could, of course, exploit the API functions in the broker that corresponds to the intercepted APIs. Because you say, when the IPC message is sent, then here you have an API that corresponds to the intercepted API, Win32 API, and then that forwards the call. So you might have some vulnerabilities in those APIs here. And that's what you want to do. Once you gain control of the execution flow here, you need to exploit a vulnerability in API here to gain control of the execution flow here. Right? This is the goal if you're going to use broker APIs. Then you can want to game the policy engine in order to do things that you're not supposed to do. And it's actually what the exploit that we released do. You may want to exploit vulnerabilities in an IPC framework, because there again, this IPC system works on a client-server model. So you have the client here, the server is here. So there might be some vulnerabilities in the server that you could exploit. Because if you gain control of the execution flow here, then you can craft whatever IPC message you want and possibly exploit some vulnerabilities in the server. Named object squatting attacks, which this is traditional. I'm not going to cover this here. A very important attack avenue is the plugins that were not sandboxed for compatibility reasons. A lot of plugins actually cannot run well with the sandbox. So the plugin developers chose to have them run outside of the sandbox. So if you exploit plugins, then you're out of the sandbox. And probably more, which will be discovered by security researchers. So yes, it's just for kernel land. The basic thing that you can do is messing with the token pointer of your sandbox process and have it point to the token of another process with more privileges. So now I was speaking about broker APIs earlier. I briefly mentioned intercept Win32 APIs as an example. Create file is a Win32 API that is intercepted, hooked. You don't have only these APIs in the broker. As a matter of fact, you have three types of APIs. Win32. Then you have the APIs that provide service Adobe Reader needs. For example, executing a file out of a whitelist. things like this. And the third category is APIs that pop up a confirmation dialog. For example, when you disable manually the predicted mode, then it pops up a confirmation dialog that says you really want to do that. All the three categories are interesting. But focusing on broker service APIs, so category number 2, it's interesting because category number 1 has probably been scrutinized quite a lot because it all comes from Google Chrome. Plus, Adobe continuously add broker service APIs. So the more they add, and the more you have to audit. See, from one version to the other, they added like 10 broker APIs. The third type of broker API is interesting too, with that dialog that pops up. Actually, we started from here because we found it interesting that if we could at first pop up that dialog without user interaction, then we get one step closer to evading the sandbox. Granted, the user might click yes, but it's not really the point here. The point is that if we can do that, means we can communicate with the broker and do basically what we want. So we will use this example later as a practical application. So what we have to wonder as security researchers if we want to audit that sandbox. 2 questions. Are there logical flaws, weaknesses that could be leveraged to circumvent all the restrictions, which is the approach taken by the exploit we will release later? And are there memory corruption vulnerabilities in the broker process? So to do that, first we have to look at the IPC channel mechanism. Basically, when the sandbox process, which is the client in that case, wants to send an IPC message, it has to seize a channel, writes data in a buffer, then signal a ping event, and wait. It's all synchronous, so it blocks. The server receives that ping event, that ping signal. It fetches the data from the buffer, dispatches to the broker. That the broker retrieves the tag and say, okay, this is this tag, so this means it's the sandbox process wants to call create file. Writes result in the buffer, signals the ping event. The client is notified, retrieves that data, and frees the channel. Programmatically speaking, what does that mean? To my mind, it means that at some point, the broker must register a callback function into the IPC server. How else would the server notify the broker, send the IPC message to the broker? In the Google Chrome implementation, you find the function thread provider register wait, which is basically the function used by the broker to register its callback. And the callback function is called thread ping event ready. And it has an important parameter called service context. So very easy. When the server receives a ping event, it retrieves the IPC message, it calls back into the broker, the thread ping event ready function, with as a parameter the IPC message and the service context. In the Adobe Reader 10 implementation, the function to register the callback function is called register wait for a single object. So once you find that one, and you put a breakpoint on it, for example, in the debugger or disassembler or whatever, like IDA, then you have access to the structures that are pointed to in the parameters. Specifically, the service context structure is very interesting. It has, of course, a pointer to the channel buffer, and it has also a pointer to a structure of dispatchers. Now, dispatchers are small structures made of a tag that identify the API function, a list of type of parameters, and the address of the handler. So it's the final step before calling the actual broker APIs. The actual broker APIs are the handlers of the dispatchers. So ping event, retrieve the APC message, send it to the callback function. The callback function looks into the service context, retrieve the tag from the APC message, sees the tag, it matches the tag with the corresponding dispatcher, and calls the handler in the corresponding dispatcher. This is how it works. So it means that, so this is a dispatcher in memory. So you can see here the tag, and here is the handler address. So it means that if you follow the dispatcher structures, but then you can map the whole broker APIs because you have all the entry points. You have the tag and the entry points of all the broker APIs. Yeah. So all you need to do then is to look into the APIs and see what Win32 API or what a broker service API it really is. So it can match tags and client APIs. Another way to do that is to I mentioned earlier that all the Win32 APIs are hooked in the Sandbox process. So if you find the function that is used on startup to hook those functions and use the cross-reference function in IDEA Pro, for example, but then you will find all the APIs that are hooked. Then you can match them with tags afterwards. Also, the characteristic string acro win main sandbox. If you look into the client, it allows us to find an array with all the tags for different APIs. For the broker service APIs, not the Win32 APIs. So for example, we found in a service context structure a pointer to the dispatcher structures. And one of these dispatchers has tag 3E. If we follow the handler address, then we find out that pseudocode. So basically what it does, it pops up the confirmation dialog, right? No, it's not that one. No, that one, yeah, that one. Pops up the confirmation dialog, and if user clicks yes, it sets a registry key, which disables the sandbox. So if we can set that registry key, then we practically evade the sandbox. So let's do some practice. What you can do at that point, you find a place in memory, and you craft an IPC message. This is the tag that you want to call. Remember, an IPC message, basically you put a tag and the parameters of the API you want to call on the other side. So we craft that IPC message. We put a breakpoint on the function doCall on the client side, which is the function that is used to send the IPC message. When we reach the breakpoint, we modify the IPC message argument, which sits at ESP +4, and we replace it with a pointer to our own crafted IPC message. And that way, and then we resume execution, which pops up the confirmation dialog. So that means we managed to talk with the broker. and call some service broker service APIs that are not supposed to be called without user interaction, actually. Then we can look at another tag, 43, which is interesting because it means open HTTP link using the default explorer, which runs with high privilege. So then again, we craft the IPC message with the tag, the argument, which corresponds to a malicious URL. This file, basically the file we point to is a proof of concept various file. It just does some modifications in the OS to prove that the file had the privilege to do that. So it's very basic, just use for the example. So same, we put a breakpoint on do call. We modify the pointer, which sits at ESP +4, to point into our crafted IPC message. Then we resume execution, and then this pops up. Again, the user might click run, but it's not the point. The point is just to show that we can communicate with the broker like we're not supposed to do. So now that we have access to all the broker APIs, because we can list them in memory via the context structure and dispatcher structure, why not auditing them? Why not looking if there are some memory corruption vulnerabilities inside? And this is not very difficult because we have the addresses, we have the parameters, thanks to the dispatcher structure. So we just need to automate that. Turns out that Michael Sutton described the in-memory fuzzer in his book, which absolutely fits our requirement, but besides it's open source. So what we did is just configuring that open source fuzzer to attach to the Sandbox process and do those steps. It's in Python, by the way. So the whole Python code is inside the white paper. If you're interested, it's very rough. What matters is the idea behind, not really the code of that fuzzer. So with some debugging library, you put a breakpoint. You take a snapshot of the process right before the IPC message is sent. Like we did manually earlier, you stuff fuzzing data into the IPC message. So the tag you want to edit, then parameters according to the types of parameters you want. Then you resume execution. The IPC message gets sent. You wait for the broker process to handle the IPC message. You hope that it's going to crash, which means you found a bug somewhere. And if not, you restore a snapshot of the Sandbox process, and you start it again until all the fuzzing data is exhausted. But you don't have to reinvent the wheel. I mean, you can use libraries with fuzzing data. So and have smart fuzzing data. So yeah, we'll do a quick demo of that actually. So if we want to audit the tag 43 API, broker service API, which is open a link in the default explorer, I configured what is that? The Python script. So we open a PDF like so. And then we open the fuzzer. So it sets the breakpoint, take the snapshots, and the proof that it works is that it tries to open URLs in the browser. See? I set it to open send one IPC message every 5 seconds. So it's gonna try to open that every 5 seconds. Of course, in a frame of a real auditing job, you can do that much faster. We did not find any crash in that particular API, but it's not the point of the paper. I mean, it's just to show how you can audit those broker APIs, right? Besides, we didn't have any smart fuzzing data, so you can start all over with some smart stuff. It should be fine. So now for the vulnerability that we found in the course of our research. It was patched by Adobe in September 2011 due to our responsible disclosure action. And it turned out that Marquis and Impulse from IBM also found this vulnerability at the same time. As I said earlier, the vulnerability is not mess with your mind. As I said earlier, the vulnerability is more like a shortcut. It doesn't try to exploit memory corruption vulnerability in the broker process to gain control of the execution flow outside of the sandbox. Rather, it tries to game the policy engine. The policy engine has a whole set of rules. Some of them are dynamic rules, added dynamically. On startup, for example, those two rules are added. So you have this rule that allows everything under the registry key Acrobat Reader 10.0, and then you have that rule that denies everything under that specific key. So basically, this means you can write any registry key that you want under this, unless it's otherwise denied by another policy, which is the case here. Of course, we've seen earlier that to disable the sandbox, you just need to add a registry key here, a Boolean be protected mode. This is what the confirmation dialog that pops up does if you click yes. So we want to game those policies. We want to create a registry key with the Boolean be protected mode here. And we want that this registry key matches this rule, but does not match this rule. It's the only way to get through, right? What could be the registry key that would match the second one and don't match the first one? Here's a magic string. Pretty easy, actually. You put 2 slashes before privileged. What does it do? The catch here is that Adobe Reader processes uncanonicalized strings. So when it compares 2 strings, it does so byte by byte. So when you input that string into the voice, when you want to create that registry key, it is sent to the policy engine, and the policy engine is going to compare that string with the strings of the policies. It does so by comparing byte by byte. So it's going to compare until then. It matches, so you're good to go. Then it's going to compare until then. Then it finds another slash, so it doesn't match. Match, no match. You get through. You get through means the magic string is sent to the kernel. NT create registry key or whatever. And what does the kernel do? It canonicalizes that string. Means it removes the extra slash, backslash. And so you effectively create that be protected mode Boolean, which effectively disables completely the sandbox permanently. This is what happens in detail. You get a create key request to the broker process, checks with the policy engine. As I said, matches the second rule, doesn't match the first one, so you're good to go. Send to the OS. The OS return the handle of the registry key. And in the Sandbox process, you create that Boolean and disable permanently the Sandbox. The patch from Adobe for that vulnerability is just stripping off the extra slash. Now, maybe there can be other symbols that are stripped off by the kernel. I don't know. Up to you to find. I have a little video that shows this happening. Don't have all the material to do that one. So we open the reader. This means version in Chinese, and the version is Adobe Reader 10. So then we open our exploit file. Oh, yeah. So I want to show the privilege of that process. So yeah, the second process here is the Sandbox process. So it runs with limited privileges. So then you open the exploit first time. So it crashes and it disables the Sandbox permanently. So when you open it a second time, then you just get free. Oh. Okay, we'll check the privilege level of the calculator that we launched to see that it went with reasonably high privileges, which means we are precisely out of the Sandbox. And we show the registry key that was modified, that was created, be protected mode, that one. That disables the Sandbox permanently. For the example, we also dropped proof of concept virus file inside the Windows folder. And if you look at file properties, you see that's just been created. At the same time. So what we really did here, first of all, we exploited a vulnerability inside the PDF principle, classical Adobe Reader vulnerabilities. It's CVE 2001-3232 in the demo. We bypassed the EPA by using heap spring and return ROP. You could do it in other ways, like using heap function, GIT, my colleagues actually use flash action script exploit, etc., etc. Then here we took a shortcut. Instead of having to find an exploit inside the broker process and bypass everything, then do local privilege escalation, just game. the policy engine. And we went free. This is Eric, actually. In his tracking trip or whatever. Yeah, so the point of all that is that, of course, the sandbox is going to be considered a panacea. It makes things more difficult for attackers, but still there are some attack avenues. This work is important because I think more and more products are going to integrate that kind of sandboxes in the future, so you could reuse everything in that paper to audit those software. And that was pretty short, so we have time for questions. Any question? Okay, then thank you.